Welcome students to the third lecture of Design of Concrete Structures. So here we will start with the theory of reinforced beams. First we will take a simple example of a simply supported beam. So consider a simply supported beam of length L and depth D with a transverse load of W. Now this load by default is considered as UDL because none of the structure experiences point load on the beams. There can be an additional load of point load on the beam, but it will be in addition to the UDL that has been transferred from slabs to the beams. Okay, so when we say load on the beam or load on the slab, by default it is a UDL. We do not draw it every time, but it is considered as a UDL. So here also it is a uniformly distributed load. We also mark something called as neutral axis. We will understand this term neutral axis soon. So once the beam is loaded with load W, it gets deflected and it looks something like this. So there is support and it is deflected in this way. So the deflection is 0 at the ends, that is at the support, and it is maximum at the center where it is not supported. Now, in this beam, in this position, the beam will experience compression. All the parts will come close to each other and it will experience compression. Similarly, at the same time, this part experiences tension as the molecules go apart or away from each other. So there is compression here and there is tension here. So as we know, we have already discussed in lecture 1, concrete takes care of the compression and steel takes care of the tension. So here we provide steel bar in the tensile zone or where the tension is more. And we need more of concrete in the compression zone or where the compression is more. So a neutral axis is basically a line that divides the beam into two zones, that is compression zone and tensile zone. Okay, so the steel is provided at the bottom of the beam, that is below the neutral axis, because this portion of the beam experiences tension, and here we need more of concrete as this part experiences compression. We'll just see the same concept for a cantilever beam. Okay, so consider a beam of length L, depth D, and again the load W. Again this load W is a UDL. Okay, and then there is a neutral axis drawn. So the deflection diagram for this particular beam will look something like this. I am talking about deflection and not bending moment. Okay, so just understand the difference between deflection and bending moment properly. Now in this, what happens is this portion of the beam undergoes tension. Okay, and this portion undergoes compression. So now we need to provide steel where there is tension, so it is above the neutral axis. So the steel bar is provided on the top of the beam, that is above the neutral axis, and here we need more of concrete as there is compression. So understand the concept of tension and compression first. Once you know this, you will know where you have to position the steel. So basically the most important part in this analysis is to find out the position of neutral axis. It is not always d by 2. It is not always at the center. Depending on the depth, depending on the type of load that comes on the beam, and depending upon the stress and strain of the material, the neutral axis position within the beam will change. It is not d by 2. Here I have drawn it as a center, but it will not be d by 2 always. Okay, it can be d by 2 but not always. So basically we have two types of beams. So in both the cases that we saw just now, steel reinforcement was provided in the tensile zone only. Such beams are called as singly reinforced beam or singly reinforced sections. So from the name itself, you can understand that it is singly reinforced. A single zone is reinforced. There is reinforcement only in one part of the beam. So it is called as singly reinforced. The other type is if reinforcement is provided in tensile zone and in compression zone to carry compressive stresses, it is known as doubly reinforced section. Okay, so sometimes we have to design the beam in such a way that the steel has to be provided in compression zone as well as in tensile zone. So such kind of beams are called as doubly reinforced beams or doubly reinforced sections. So we are basically going to learn SRS and DRS in detail, that is analysis and design, in this particular chapter. The first important thing that we need to know is something called as modular ratio. We have to consider a composite structure to understand what is modular ratio. Why composite structure? Because any beam or any structure that we will be considering, that is beam or column, it will be a composite structure because we are using concrete and steel into it. Okay, so here I have taken a small example, a steel rod and a concrete rod. Okay, they are attached with a plug of length, the rods are of length L, and there is a point load or compressive load that is exerted from both the sides of the structure. Okay, so let here ES, that is modulus of elasticity of steel, be ES, modulus of elasticity of concrete be EC. Area of cross section for each bar is equal to A, that is capital A. PS is load carried by the steel, PC is load carried by concrete. So then the total load will be obviously P equal to PS plus PC. So total load P is divided into 2, that is load carried by steel and load carried by concrete. From compatibility, delta is equal to delta S equal to delta C. Now what is this delta? It is a shortening of each bar under external load. As there is a compressive force or compressive load exerted from outside, obviously these two bars will undergo some change. And because it is compression, it will shorten. So this delta is considered as delta S equal to delta C. It is same as the total load exerted from both the sides is same. Therefore, the total deformation will be equal to PS into L upon A into ES. You have already learned this equation PL by AE in mechanics of material. So I need not repeat this. You should understand what is this equation used for. So this equation here we have considered for steel and concrete separately. As the load taken by steel is different, that is PS, L is same for both, A is same for both, and modulus of elasticity for both the material is different. So we'll have to write it as PS into L upon A into ES equal to PC into L upon A into EC. Or we can again write this as PS upon ES is equal to PC upon EC. A small note, deformation for a simple homogeneous bar with a constant cross section and a constant applied load. So here the cross section is constant, that is A, and the load that is applied is also constant, that is B. In this case only we can consider this particular equation. So from equation 1 and 2 we get PS is equal to P into ES upon EC plus ES, and PC is equal to P into EC upon EC plus ES. So here using equation 1 and 2 we have written these equations. Also I have written the same equation as M into P upon M1 plus M, and the next it is P upon 1 plus M, where M is considered as ES upon EC, that is modulus of elasticity of steel upon modulus of elasticity of concrete, and this particular ratio is called as the modular ratio. Equation A and B, just take a note that equation A and B, it is seen that load carried by steel is M times load carried by concrete. So this particular M, so load carried by steel is M times load carried by concrete. Load carried by concrete is P upon 1 plus M. So this is basically, if you consider only this part, it is PC. So PS is equal to M times PC. Now we learn a small concept, or you should understand the concept of equivalent areas of composite sections. Composite sections are sections which are made using two materials. So here is a simple beam, cross section of a beam, okay, or you can consider column because I have shown the reinforcement in 4 corners. So this is a cross section of a column with 4 bars here. These are the steel bars that are provided. So total area of steel is AS. So area of each bar is AS by 4. So this is AS by 4, this is AS by 4, this is AS by 4, this is AS by 4. The remaining portion is area of concrete. So this is area of steel, this is area of concrete. Now, the amount of steel that you provide or put in the section, that much amount of concrete has to be removed. So here I have shown a hole, and this is the reinforcement that is provided here. So it is M times AS into 4. As we already discussed, it is in the previous slide that load carried by steel is M times load carried by concrete. So now if we replace this concrete by steel, it has to be M times its area. Is it clear? So we remove this concrete and we will put this bar into it. So it will be M times the area. So this is the transformed section of the concrete. So total area of section is A, which is equal to AS plus AC. And after this, considering the equivalent area, we get the equation as AC plus M times AS. This expression is called as equivalent area of the section in the terms of concrete. You do not have the derivation of this particular equation. That's why I have not done this in detail. You have to only know the final equation and the concept of equivalent area. We are just going to use this equivalent area concept to do the further analysis. You do not have the derivation in detail. Thank you.